let's recap what we learned by doing problems 3 and 4. And so in problem 3, we applied the combo of the triple product, the expansion rule, and also our Maxwell relation and that allowed us to figure out what this dt over dp at constant h partial derivative was. Right? And so this partial derivative is a fairly famous one. It's called the Joule-Thomson coefficient, and it's useful for whenever you have to analyze flow through a valve. Okay? So we derived a functional form of dt dp constant h. And in problem 4, we actually applied that functional form. Alright, and so in problem 4, we dealt with a van der Waals gas in which the interactions were turned off. Right? And so by turning off those interactions, that simplified the math, because that allowed us to just rewrite our equation of state explicitly for volume. And then in the Joule-Thomson coefficient formula, it was very easy to just take dv dt at constant p. Right? But this was a hypothetical situation and a very contrived situation, because for almost all chemicals that follow the van der Waals gas equation of state, A is not going to be 0. In fact, A is typically a very significant term. Alright, and so in that case, if A is not 0, we wouldn't have been able to just rearrange our equation of state very easily, or at all. So been able to write explicit equation for dv dt constant p. Alright, and so if you run into that sort of situation, so for equations of state where v cannot be written explicitly, to get around or to get over this barrier, you would actually have to do more thermodynamics of calculus, or calculus of thermodynamics. So you would have to apply an extra triple product rule. To rewrite your equation as like the ratio of partial derivatives of pressure. All right. So you'll get practice doing that later. In any case, though, so we did these problems in the context of looking at gases and stuff. But this same strategy, also applies for when you're dealing with liquids. And when you're dealing with a liquid, a lot of times this partial derivative, dv dt at constant p, is written in terms of what we call the isothermal compressibility. So another named derivative that we've talked about before. So isothermal compressibility, alpha v, by definition is this. Constant pressure. And so, if you just solve for dv dt constant p, you could write it like this. And the reason this form is useful, especially for liquids, is you could actually just measure this alpha v parameter through an experiment or something. And so with that Joule-Thomson coefficient, JT, you could write it like this. And then you could even factor out the volume. T alpha V minus 1. Right, and so like I said, for whenever you're dealing with liquids or even solids, actually, a lot of times it's more convenient to write your Joule-Thomson coefficient like this.